Hey everybody. Alright, so when you're thinking about the effect that atmospheres have on the temperature and the climate of a planet, there's a few moving parts here. Fundamentally, though, the greenhouse effect and the effect of temperature are all about a planet warming up until the energy coming down from the planet's parent star, which, if we're talking about the Earth, that's the sun, right? The temperature of the planet is about the planet receiving light from the sun, warming up until the light that escapes the planet back out to space comes into equilibrium with the incoming energy. So if we look here, right, add up all the arrows that leave the atmosphere. How is light, and therefore energy, how is energy leaving the Earth? Well, it either reflects off the surface, or it reflects off the atmosphere, or it's emitted by the ground out to space, or it's emitted by the atmosphere back out to space. So if we add up this plus this plus this plus this is what? This is 30 watts per square meter plus 77 plus 40 plus 195 watts per square meter. You add that all up, and it comes up to 342 watts per square meter, which is exactly equal to the energy coming in from the sun. Right? The Earth has warmed up until the 342 watts per square meter coming from the sun is balanced by all the ways that the energy is leaving the Earth, and the planet stops warming and reaches an equilibrium temperature. If we add up all the arrows absorbed by the Earth absorbs energy from the atmosphere from the atmosphere here and from the sun here. And that's the 168 watts per square meter here, plus the 324 watts per square meter here. And that adds up to 492 watts per square meter. How does that compare to the energy from the sun? Well, that's less, right? The Earth is absorbing more energy than the sun is actually shining on us. It's less than the 342. How can the Earth be absorbing more energy than it is receiving from the sun? Well, because it's receiving the light from the sun and also the light given off by the atmosphere. So that is greater than the energy from the sun. Where is the Earth absorbing that energy? Where is the Earth absorbing more of its energy? Well, it's getting 168 watts per square meter from the sun, 324 watts per square meter from the atmosphere, so it's actually absorbing most of that heat from the atmosphere. How much energy is being absorbed by the atmosphere? Well, the light comes from the sun and gets absorbed by the atmosphere here, but also the continuous spectrum given off by the surface of the Earth gets absorbed by the atmosphere here. So if we add up the 67 watts from the sun plus the 452 watts per square meter from the surface of the Earth, that comes to 519 watts per square meter. So the atmosphere is absorbing energy here and energy here more than any of these other two. Compare this to the energy from the sun. Yeah, this is greater. The atmosphere is absorbing more light than we are receiving from the sun. Why? Because the atmosphere is also absorbing the light given off by the Earth. Where does most of this energy come from? It comes from the Earth. So the Earth is absorbing more energy from the atmosphere, and the atmosphere in turn is absorbing more energy from the Earth, right? Every second, the Earth is giving off light, and most of it gets absorbed by the atmosphere. The atmosphere warms up, and then the atmosphere gives off light. Some of that energy escapes from the atmosphere out to space. Some of the energy is emitted by the atmosphere and reabsorbed by the ground. And which one's bigger? 324 watts, 195 watts. Most of the light given off by the Earth gets reabsorbed by the atmosphere. The atmosphere then warms up and gives off its light, and most of that is reabsorbed by the ground. And so the energy just keeps on cycling back and forth, right? The Earth gives off energy, and the atmosphere sends most of it right back down. Absorbs more energy, sends most of it right back down. This is the greenhouse effect, right? That's the greenhouse effect, where the Earth is trying to cool itself off. And so it sends more energy out to the atmosphere. Most of that gets sent back down from the atmosphere back down to the ground over and over and over until finally some light given off by the Earth either escapes through the atmosphere to space or it's emitted by the atmosphere out to space. But as long as that energy is just bouncing back and forth between the ground and the air, it's going to warm up the Earth. And that's the extra temperature that a planet has from the greenhouse effect. So what's the total energy emitted by the atmosphere out to space? That's the 195 watts per square meter. What percentage is that of the total radiation from the sun? So the atmosphere is emitting 195 watts per square meter out into space. The amount of total energy coming from the sun is 342. So 195 divided by 342 is 0.57 or 57%. The more light, the more energy an atmosphere absorbs, the hotter the atmosphere is going to heat up, and therefore that's the extra heat, that's the extra temperature added to a planet from the atmosphere reabsorbing it and sending it back down to the ground. The extra heat that the planet retains as that energy is being slowed down before it can finally escape out to space. So if the Earth's atmospheric absorption is 57%, then the greenhouse effect warms up the Earth by an extra 30 degrees Kelvin. So the effective temperature of the Earth is 254 Kelvin, right? Remember, the effective temperature is basically a model of the temperature where there is no atmosphere, and either the energy is absorbed or reflected. But if that energy is emitted back out to space, but it gets slowed down and retained by the atmosphere, that's going to add the extra temperature from the greenhouse effect. So if you take the effective temperature plus the extra temperature from the greenhouse effect, that's going to be a calculation that'll give you a much more accurate prediction or explanation for the actual temperature of a planet. So then the actual surface temperature of the planet is 284 Kelvin, which makes a lot more sense because at 284 Kelvin and under 1 atmosphere of pressure, water is a liquid, which is how we can have all of the lakes and oceans and rivers that we have here on Earth. 254 Kelvin is way too cold. If this were the temperature of the Earth, all the water would be frozen. But you add that little bit of extra heating from the greenhouse effect, and all of a sudden the Earth warms up to be a nice temperate place that can have liquid water. Okay, but what's actually absorbing the light? What kind of light? And what kind of light is being absorbed by the atmosphere, and what gases in the atmosphere are doing the absorbing? Well, what two types of light does the sun emit most? Well, the sun emits mostly visible and infrared. Those two numbers there. What type of light does the Earth mostly emit? Yeah, most of the Earth's continuous spectrum is in the infrared. So the sun gives off a lot of infrared. The Earth gives off mostly infrared. And the infrared light is what's actually being absorbed by, there you are, by the atmosphere. Right? Visible light has an easy time getting through the atmosphere. Our atmosphere doesn't absorb much visible light. But infrared has a harder time getting through the atmosphere. Infrared gets absorbed mostly by what? Well, mostly by carbon dioxide, methane, and water vapor. So, what are the three gases that are absorbing most of the infrared in the atmosphere? Water, carbon dioxide, and methane. Which of these greenhouse gases absorbs the most? Well, 25% is the largest percentage we've got. That's mostly the water vapor. Which, as it says, is temperature dependent, right? Sometimes there's more water vapor in the atmosphere, sometimes there's less. The other two gases, which one contributes? Of the other two, carbon dioxide or methane, which one absorbs most of the infrared? That's the carbon dioxide. Where does carbon dioxide come from in the atmosphere? Well, carbon dioxide comes from aerobic respiration, right? Animals exhaling carbon dioxide. Carbon dioxide can also be emitted through volcanoes and geologic activity. But that hasn't changed much, right? The non... how should I say this? The amount of geologic activity hasn't increased very much in the last few hundred years. The amount of CO2 emitted by animals hasn't increased that much. The one thing that has increased is human technology. Human technology that burns hydrocarbons, and when you fuel a combustion reaction, that emits carbon dioxide. So, what is one way that carbon dioxide is increasing in the atmosphere? How shall I want to put this? Let's just say, I was going to say combustion, but why make it more technical than it needs to be, right? The burning of hydrocarbons. What are hydrocarbons? Well, hydrocarbons are substances, materials that are made of a lot of carbon and hydrogen, like gasoline, coal, natural gas, like methane, right? Carbon and hydrogen, right? Methane is a hydrocarbon. Any combustion reaction takes hydrocarbons and oxygen and burns it to make energy, and it produces carbon dioxide. So as the carbon dioxide in the atmosphere increases, what does that do? Well, let's go back to our greenhouse effect here, right? If the atmosphere is now thicker with more carbon dioxide, then it's going to absorb more than 24% of the infrared. So that means the infrared light coming from the sun that gets absorbed by the atmosphere, and the infrared that's emitted by the Earth's surface, more of that is going to get absorbed. More energy is going to be absorbed from here and from here. And if the atmosphere absorbs more energy, then the atmosphere is going to warm up. And if the atmosphere warms up, it's going to send some of that energy back to the Earth's surface and some of it back out into space. But if you look at these numbers, most of it's going to go back to the ground. So if that energy gets sent back to the ground, then the ground warms up. Right? And then if the ground warms up, then the Earth is going to give off more light. And most of that light is going to get absorbed by the atmosphere. So it's going to send even more of that energy back down to the ground. And so by making the atmosphere thicker with gases that absorb infrared, like carbon dioxide, you're strengthening this effect, right? More energy gets absorbed by the atmosphere so that it gets sent down to the ground. If the Earth's surface warms up, then it's going to send more infrared back out so that out into the atmosphere so that it can be sent back down. And that's going to warm up the Earth even more. So the Earth gives off more light, and more of that energy gets sent back down to the ground. And then it'll heat up the Earth even more, right? And as long as the energy just cycles back and forth, the Earth is going to get warmer and warmer and warmer until finally the energy can escape out into space from here or from here. But while the energy is trapped here before it escapes, That's going to heat up the Earth, and that's global warming. Right? That is the increase in the global temperatures from the extra carbon dioxide being put in the atmosphere. And it doesn't take much. Look at these numbers, right? The amount of carbon dioxide in the atmosphere today is only 0.041%. That's more than it used to be. 100 years ago, it was more like 0.03. It only takes 0.04%, and that absorbs 24% of the infrared, both the infrared coming down from the sun and the infrared coming up off of the Earth. So small changes here become big changes here. And so adding a little bit more carbon dioxide to the atmosphere from the burning of hydrocarbons from human technology, that is a big enough change. Even though it's a small percentage, it's a big enough change to increase this number and warm up the Earth, which is what causes the rising of global temperatures like we're seeing today. This isn't just an effect on Earth, right? We're studying the effect on Earth, but this is happening on any planet that has greenhouse gases. What's a greenhouse gas? A greenhouse gas is any gas that absorbs infrared. So, if a planet's atmosphere has water vapor, carbon dioxide, methane, or other there are other greenhouse gases that we don't see here on Earth. But if there are gases in the atmosphere of that planet that are good at absorbing infrared, you're going to have the greenhouse effect. You're going to have a larger percentage of atmospheric absorption raising the temperature of the planet by that much. It seems more complicated than it is, but it's really just this simple, right? By making the atmosphere thicker so that it absorbs more energy, it's going to absorb more energy, send that energy back to the Earth's surface, and warm up the Earth's surface. That's the greenhouse effect. It's really not that. It's not much more complicated than that. We're getting into the details here, but fundamentally it's just gases absorb light. We've seen that with the absorption spectra, right? And if the absorption lines in the gas are in the infrared, then you're going to get the greenhouse effect. It's not much more complicated than that. So let's see how this plays out on some other planets. All right. Kepler-62f is orbiting a star with 0.21 solar luminosities. It's orbiting at a distance of 0.718 AU, and the planet has an albedo of about 0.2. So, since I've got my spreadsheet to calculate the effective temperature already made up, let's see here. All right. Alrighty. 0.21 solar luminosities. It's orbiting at 0.718 AU with an albedo of 0.2. Alright, then that planet has an effective temperature of 210. I'll just round to the nearest degree. That's fine. Alright. And if its atmospheric absorption is 75%, then with an atmospheric absorption of 75%, that's going to add an extra 100 degrees from the greenhouse effect. So then the actual surface temperature of the planet is the effective temperature plus the extra greenhouse temperature gives us 310 Kelvin. If the planet has a temperature of 310 Kelvin and an atmospheric pressure of 1 atmosphere, what is water like at 310 Kelvin under 1 atmosphere? That's a liquid. So this planet could have liquid water. How about Kepler 452b? Let's see. That is a 1.2 solar luminosity star. The planet is orbiting at a distance of 1.05 AU. It has an albedo of 0.1. All right, so that's an effective temperature of 277. It's got an atmospheric absorption of 80%. So again, we're at this last rank here. So an extra 100 degrees from the greenhouse effect means that this planet's actual temperature is going to be closer to 377 Kelvin under 1 atmosphere of pressure. What's the water like there? Well, let's go back and look at the phase diagram of water. Where did I put you? There we go. Alrighty. So, 377 Kelvin. So right about there. And 0.1 atmospheres. So 300 and under 0.1 atmospheres. 377.1 atmospheres. Yeah, that puts us right about there. So that's a vapor. So that planet, too hot. Too hot, not enough atmospheric pressure. Any water on that planet will be evaporated. All right, how about Coro 7b? .406 solar luminosities, 0.0172 AU, an albedo of 0.9. Oof, 953 Kelvin. 953 Kelvin, that is hot. And an atmospheric absorption of 5% means 5% means it's only going to add, that's a weak atmosphere, it's only going to add 10 degrees. So that planet is more like 963 Kelvin. 963 Kelvin under... Oh, our graph here only goes up to 600. Okay. 963 Kelvin under 0.001. Well, 0.001 atmospheres and a temperature way out here, out past that away. Yeah, safe bet. That water is way too warm. Not very much atmosphere. Definitely evaporated. How about Kepler 22b? 0.79 solar luminosities, 0.849 AU, 0.3, and albedo 0.3. So we're talking, 260 Kelvin. Alrighty. 260, around to 261. Okay. 45%. 45%. Okay, gets us up into that plus 30 degree range. So then the temperature of that planet is more like 291 Kelvin. 291 Kelvin under 5 atmospheres. Let's see here. 291 Kelvin under 5 atmospheres. 1, 2, 3, 4, 5. Yeah. Okay. Water, liquid water it is. So this is one of the ways to get a handle on, now that we're finding all of these exoplanets, right? All 4 of these are exoplanets. Now that we can calculate the effective temperature, and if we can estimate how strong the greenhouse effect is, is it kind of weak, in the middle, or really strong? We can add those 2 effects together to get a much better prediction. Like I said before, the effective temperature is a a decent first guess. It's a good estimate for what the temperature of the planet could be, but once you add in the effect of the atmosphere, okay, this is going to give us a much better explanation, or a much better prediction for what the temperature on the surface of the planet really is. And now we know, or now at least we have a really good idea about which of the planets that we're looking at are more likely to have liquid water, like Kepler-62f and 22b, and which ones should we not spend too much time studying if we're looking for planets that have liquid water. All right. So again, putting the calculation to calculate the effective temperature into our spreadsheet saves us a lot of time, and then all we need to figure out the strength of the greenhouse effect is to look it up on this table, and then add those two together, and we'll have the actual surface temperature of the planet. All right. I hope that's making some sense and helping you out, and have a good day, everybody.